Hello everyone. So today we are going to learn about simple harmonic motion, and this is in A2. The course we're doing right now is 9702 of Cambridge. So to really understand what really simple harmonic motion is, in the first part we're going to prove the equation of simple harmonic motion, and to do that we need to learn what exactly is the simple harmonic motion. So a simple harmonic motion is a type of oscillation or periodic motion, right? So it's a movement in a complete cycle where the acceleration is directly proportional to the displacement from mean or equilibrium point, and is always directed towards that point. Now, what it really means is that the acceleration is directly proportional to the displacement from the equilibrium point, and it is always directed in opposite direction to the displacement. So that's the reason I have put a negative sign here. Now, it's the same thing as, let's suppose if there's a toy car that is oscillating to and fro in this situation, and you might see that at this point it is at equilibrium, and when it moves to the extreme point towards the right, if we say that's the positive displacement, then as it goes towards that, you might realize that its speed is going to decrease because the acceleration is acting in the opposite direction to the displacement and is directed towards that equilibrium point that we've written here. Now, if we look at this part where it moves to the extreme left, and then we realize that x is negative, so it's moving to the opposite direction that we took as positive, and then the acceleration will try to restore it to its position, and it is going to act again towards the same direction or towards the equilibrium point. So that's our definition. Now, this definition, some people say, in a lot of books called restoring force as well, because essentially this is the force that tends to bring an object back when it's oscillating. Now, what exactly really oscillation means? So oscillation means that basically you start from a point and then you go back and you complete that in a whole cycle or something, right? Like for example, in this point, it goes forward and then backward to the same point, and then moves to the other side and then backward to the same point. So basically, that's how it completes the cycle. So it's just a cycle. So this equation, if you open this proportionality sign up, so we need to put omega square, and this omega square is the angular velocity, and you might have already seen this formula in circular motion, and that is this. Anyway, so to prove that this is something like this, so we need to learn that we need to somehow draw the circular motion on some type of axis, and one of the best ways to describe is using a circle, because essentially a circle can tell you about one complete oscillation itself. So let's suppose that at this point this is a equilibrium point, and I just matched it with a circle, and then we have 4 different paths to it. So when the object is going to move at any certain cover, it will cover any theta. So you might realize that basically that's being covered because of the fact that it's moving, right? It's moving in a circle, or we assume it, we just explain it through the circle. So after like a quarter of time period, it's going to go exactly to this point, which is this highest point. So it starts from 0, and we can put it like this. After a quarter, it's going to be exactly somewhere here. So in the next part, when it moves through a cycle of a time period, takes time period of half, so it must have gone through this point, which means if I plot it again, so it will again come to the same axis right here. Now in 3/4 of a cycle, this object is going to move from here till here, so it should be somewhere here at this point, and we can then put a marker here. Let's just put a marker exactly like here. Now again, when it's about to reach its one complete cycle, so it will go from here, it will cover this angle as well, so it reaches to the same point essentially. So at T, it's going to come at the same point. Now if I try to connect all the points the way they appear, so you might realize there's this sort of a line is generated, and this line is basically a function of sine theta. And of course, if you realize, so when it was like here, the displacement x if this is like the maximum displacement, let's call this x0, so I'm just going to write it as max displacement for our reference for all future equations. And at any x, we can find the required time or whatever. So let's call that as just the displacement at any required time. So basically, this whole thing is just going to give me an equation that x will be a function of x, the maximum displacement times sine of theta, right? Now this sine theta just tells you the ratio between x and x0, so you can just work it out yourself. Now, whereas we have learned that angular displacement is basically given by the angular velocity times t, so we can just replace that, and the equation for this equation might become x0 times sine of omega t. Okay, now so this is how you see. Now you realize that if you have a displacement x and you're plotting anything like time t, so it will give you a sine curve like this, just like a wave, and one complete oscillation will show you one wave here. And we've learned that the equation that it portrays is x equals to x0 sine of omega t. Now, so from this point onwards, you must realize that why are we doing this? Because we need to find the connection between three things. So we need to find the connection with displacement, velocity, and acceleration in this particular chapter, that how a certain oscillation, which is S.H.M, is going to behave, right? So if you're a math student, you might realize that whenever we need to find velocity, so let's just move towards the velocity. Velocity is given by change in displacement upon change in time, right? And you can actually write it as dy. Okay, we can write it as dx by dt. What it really means is just the same thing as triangles. We're going to change it. If we take the derivative of this equation, which we earlier did, of x, so we might be able to find the equation for v. Now, you don't really need to learn this. You can just remember this. You don't really need to learn the derivatives and all, but I'll just tell you a small thing, and that is that whenever you see you take the derivative of perhaps maybe sine of x, it's going to give you, you take a derivative, of y equals to sine x, so it is going to give me just cos x. And if you take a derivative of maybe y equals to cos x, it's going to give you minus sine x. You just need to remember these. Otherwise, if you remember these equations, that's good enough too. So let's just not waste time and go here. So our essential equation was x equals to x naught and then sine omega t. So if I take the derivative, which is dx by dt, so I'm just finding the change in x upon change in time, which is of course equal to velocity, then I might realize that it is going to be omega times x naught times cos omega t. So what I've done is I've just converted sine into cos because it's a derivative, and then I've just multiplied the constant with t because there's this one t here, so I've derivated the angle itself, and the equation come out to be as omega x naught. So v equals to omega x naught cos omega t. Now because this is a cos function, so if I try to make a graph of this, so it might appear to be something like this to you as a function of cos. So we can write the equation v, which is omega x naught cos omega t. Now moving on to the next part, you also know that acceleration can be found out by change in velocity upon change in time. And again, if you're a math student, you know the derivative of v upon respect to t is going to give you acceleration. Now, so the equation of v that was there was actually omega x naught cos omega t, and now we're going to find the derivative or the change in that with respect to v. So it's going to give us again minus, because we will change that, or let me just write it one by one. So we have already omega x naught times omega from the inside times minus sine of omega t, because I just told you in the previous part that whenever you multiply, whenever you derivate cos, it comes out to be minus. So ultimately we are, I'm just sorry, this was supposed to be omega, so then it's going to be minus omega square x naught and sine omega t. So that's where your acceleration lies. Now if you see, this function is just minus omega square x naught sine t, so and it's minus sine, so your graph of acceleration time would be something like this, right? So that's a and that's minus a, right? Something like that. Now one thing that you might realize is that within this graph, this is positive sine theta, and so if this is at a certain phase, then we can say within this graph and this graph there is a phase difference, and you remember phase difference from your AS level has to be 90 degree or half and 1/4 time period, whereas here the phase difference between acceleration and displacement go down. Okay, so between that and that's going to be exactly 180 degree phase difference, because of the fact that it's exactly like flipped. So that's what we got to know. Now a quick summary that we learned was that the displacement, I'm just going to write, the displacement was given by x naught sine omega t, and the velocity was given by v equals to omega x naught cos omega t, and the acceleration was given by a equals to minus omega square x naught sine omega t. Now, to prove that the S.H.M equation, which is essentially given to us as a equals to minus omega square x, and that's what we learned, okay, if this exists truly, so you might realize and you might see here that this equation and this equation has some similarities. So if you see the accelerations equation, which is minus omega square x naught sine omega t, this portion exists in this portion tall, right? So we can just put this here, and if we do that, so the whole equation can be replaced because it's equal to x, so you can replace it as x, and there you go. That's the proof of our S.H.M equation that we learned in the first place, which says that acceleration is directly proportional to the displacement, and it is always directed in the opposite direction to the displacement or directed towards the equilibrium point. So see you in the next part. I'm just going to link it up somewhere at the end. Thank you so much. Bye.